Today we are going to do the experiment number 2, and the experiment number 2 is to find out thermal conductivity of given material. So this is a stainless steel, and thickness of stainless steel is given here 25 milli, and the diameter of the stainless steel is given to you 25 milli. Okay, same this and this same thickness. So diameter is given to find out area, because heat is flowing over this cross sectional area, so we can find out area. Okay, so now we are going to find this thermal conductivity of this stainless steel. So first, so last week we did this intermediate section, we take the thermocouple out. Okay, now we are not going to use this. This is only for verification. Now we can use these unknown materials. There are 3 unknown materials. In exam, anyone will be given to you: stainless steel, aluminum, and brass, small dia. Okay, so we can find out. So today we are going to take stainless steel. So first, do the experimental setup. So this is a hot section. This is cold section, which is having thermocouple 6, 7, 8, and this 6, 7, 8 is connected here. Then I will put this stainless steel. Okay, so this projection, yes, see, not like this. Okay, it will lock, and then we'll put the hot section, and there are 3 thermocouples which are connected to 1, 2, 3. So 4, 5, there is no thermocouple. Okay, so keep this, and now lock the device. Okay, first step, make a setup, make a experimental setup. Number 2, start the water. Start the water at 1.5 liter per minute. See here now how much one approximately. It's a laminar flow. Yeah, like this. Smooth flow, laminar flow means it is around 1.5 liter per minute. No need to measure. Okay, no need to measure. Approximately 1.5 liter per minute. Don't touch here. Don't control from here and here. Only from here. Okay. Now start the water at 1.5 liter per minute. Next, make the back switches on. Make sure back switches are on. Okay. Then main switch on. Next procedure, main switch on. So make the switch on and adjust the voltage to 12 volt, 9 volt, first reading 9 volt and second reading 12 volt. Okay, so keep this on voltage, keep this on T1. So this is on voltage, and this is T1, T2, T3 on T1, and now I will increase the voltage to 9 volt. 6, 9, 9.1, doesn't matter, around 9. Okay, and we need to measure the current. So this is a 9 volt, and the current will not change. You can record the current 0.93. Okay, or you can later on we can record that. Now this temperature T1, T2, T3, 6, 7, 8, 4, 5 is not there, so no need. We have to calculate the temperature. Instead of 4, 5, we have to calculate 6, 7, 8. After 20 minutes, after steady state is reached, steady state, when there is no change in temperature with respect to time. So at least 20 minutes we will wait, and we will take the reading. Next we will make this voltage 12 volt, and we will repeat for 12 volt. And at last, make the voltage 0, close the water. Thank you. So the determination of thermal conductivity of solid. So it is the same experiment like last week, or experiment number 1, the Fourier's law verification. And now after verification of Fourier's law, we can find out thermal conductivity of solid. So write your name, ID, section number, experiment number 2. The title of the experiment is Determination of thermal conductivity of unknown material. So this is title of the experiment. The objective number 1, to find temperature distribution across given metal slab. Number 2, to find thermal conductivity of given material. Number 3, you can add one more, to study the effect of temperature on thermal conductivity, key of metal. So the experiment procedure is same, equipment description is same as before. So there are two blocks. So one, the hot section, then there is another intermediate section, and there is a third which is near to cold section, that is water, that's why it is called cold. And now water is flowing through this pipe, cooling water to carry out the heat. So this is a cooling water at a rate of 1.5 liter per minute approximately. So there are 6 thermocouples. The first thermocouple is, there is another thermocouple at a distance of 1.5. Again, there is no thermocouple in the first section. Yes, these are the 6 thermocouples. So thermocouple 1, it is T1, T2, T3, T4, T5, T6 as given. Distance between each thermocouple is, and the phase, again it is same, it will not change, 0.0075. This is 0.015. The distance between this is also 0.015. Again, this is phase and thermocouple, 0.0075. The distance of unknown specimen. The distance of unknown specimen, it is delta x, and it is a steel, so I will write here steel. Delta x steel is equal to 0.030 meter as given in the lab manual. Same like this. Distance between phase and thermocouple T4, T4 and T5, T5 and 6, and this phase is same like above. So it is same. So this is again 0.0075. Now there is a heater through which the current and voltage is passing. So it is used to heat the metal. So here current is flowing, and I can find out the amount of heat flow Q is equal to voltage into current. So I can measure the voltage and I can measure the current. So as they start heating, heat will flow in this direction downward. So this is amount of Q flowing. So same heat will be flow here, same heat will be flow here. Heat neither be created nor be destroyed. It can flow from one point to another point. So first slab, this is near to heater, that's why it is called hot section. Okay, this last slab, it is near to the cooling water, that's why it is called cold section. And inter between, this is a intermediate section. Okay, so this first is a brass material. Yes, we need to find the thermal conductivity of brass. Then the second is we choose a steel, and thermal conductivity we need to find. Again, this is a brass, and we need to find thermal conductivity of brass at a different temperature. Okay, so this is about your experimentation, and there is an explanation. Our objective is to find thermal conductivity of steel and brass, and there is a no thermocouple. In last experiment we study, there is a thermocouple here and here. There is no thermocouple now. So now we can find what is the temperature distribution in steel slab. Okay, now the Fourier's law states that the amount of heat flow through this metal bar is given as Q is equal to the thermal conductivity of material, K, area of flow, into dt by dx. Now my target is to find out K. So K is equal to Q, this A goes down, QA dx by dt. As I know, I can measure the voltage and current, so I can find Q. Q is known to me. Now what about the area? So this area, this metal slab, it is a circular in cross section. The diameter of this bar is given as 0.00025. So I can find out the area of cross section, that is pi by 4 d square. So area is known to me. Now delta x. So delta x is known to me. Delta T for T1, T2, T3 is known. I can find out K brass. Then delta T, T4, T5, T6 I know. I can find out K brass. Now steel. The temperature at the steel and hot phase, it is required to find out. And again, I should know this temperature. So if I know these two temperatures, then I can find out the thermal conductivity of the steel. So this, let us assume this temperature T is hot phase. Why it is hot phase? Because it is in contact with the hot section. Let us call this cold section T cold phase. T hot phase minus T cold phase. I know this. I can find out thermal conductivity of steel. Now look at, see here, how I can find T hot phase and T cold phase. Now apply the Fourier's law, what I shown in here. So Q is equal to K brass, because it is brass, into area into dt by dx. So I will choose the dt. I will choose T2 and T3. I will choose T2 and T3. So T2 minus T3. And I should change this distance, the distance between T and T2 and T3. It is 0.015. Okay. If I choose T1 minus T3, then I have to choose the distance between T1 and T3 is 0.03. Okay, that's addition of this. So it is up to you to choose. Now, same heat is flowing through this part downward. So apply the here. Same material, K brass. Area is same. Now temperature difference is T3 minus T hot phase divided by 0.0075 distance between this. This is same Q, this is same Q, same material, brass, this is same brass, this is brass, get cancelled, area is same, get cancelled. Now I will write the remaining terms. T2 minus T3 divided by 0.015, look at here, 0.0075 half into 2, it becomes 0.015. It is same, is equal to, what is here, T3 minus T hot phase divided by 0.0075. This 0.075 get cancelled. So what is remaining? T2 minus T3 divided by 2 is equal to T3 minus T hot phase. So I can write for hot phase, T hot phase is equal to, this goes that side, it becomes plus. Now T3 as it is. Now T3 as it is. T3. Now this comes in bracket single term as a minus, because here it is a plus. It will become minus T2 minus T3 divided by 2. This is the first equation. Similarly, I can find out T cold phase is equal to, I will ask to you how to find out T cold phase. Suppose this temperature is 80, this temperature is 60, and this temperature is 40. See, this is length is 0.015. 0.015. So what is the drop? 20. 40 and 60 and 40. How much drop? 20. For x distance, drop is 20. For x distance, drop is 20. For half distance, how much? 10. So 40 minus 10, what will be this? 30. 60 minus 40. 60 minus 40 divided by 2, that is 20 divided by 2, 10. And this is 40. 40 minus 10, 30. It's so simple. Same again, I will give you the example here. This is 40, suppose.
Okay, this is 30, this is 20, and this is 10. T4, T5, T6. What is the difference? 10. What is the difference? 10. What is the distance? 15. 15. So for half distance, what is the difference? 5. See, 10 plus 10, 20, 20 plus 10, 30, 30 plus 5. So this temperature will be 35. This is the example. So similarly, what I did, I added in 30, I added the difference. So similarly, I can write here T6 plus T6 minus T7 divided by 2. So once I know T hot phase and T cold phase, I can find delta T, delta X is given, Q no, I can find out K still. Okay, this is the procedure to find out the thermal conductivity of steel. Now experimental data, observation. So first important observation, again it will be same as last experiment. The distance between each thermocouple is 0.015. Number 2, the distance between each thermocouple and face is 0.075. Number 3, the diameter of the bar is 0.025. Number 4, the thickness of the given steel specimen is 0.025 meter. Now observation table, we'll come to the observation table. Heater current, that is I, its unit is ampere. Now second, hot section, high temperature, T1. Hot section, mid temperature, T2. Hot section, low temperature, T3. Then there is no T4 and no T5. Then there is a cold section, high temperature, T6. Cold section, mid temperature, T7, and cold section, low temperature, T8. So we'll record the readings from the, now we'll write the readings. Number 1, current is 0.95, 52.2, 50.8.
واحد يحولها على الكرنت حولها
Turn on current. How much current?
0.95.
0.95. Okay. Now tell me the temperature fast.
C1
52.2.
52.2 next.
C2
50.8.
50.8 next.
49.4.
49.4 next. 6. 4, 5, 6.
26.8.
26.8 next.
25.9.
25.9 next. Last. 58.
23.1.
23.1.
1.
Very cool. Okay. Now adjust the voltage to keep on turn on voltage.
ايوه
Yes, all temperature T1 and then increase the voltage to 12 volt.
خلي لف الفرع.
That's fast. Good. Now after 20 minutes we will record the second readings. Thank you.
1.28.
1.28 T1
87.6.
87.6 next.
85.
85.0 next.
82.3.
Next. T6
29.6.
huh?
29.6.
29.6 next.
27.9.
27.9 next.
24.6.
24.6. Reduce the voltage to 0. Keep on voltage. Reduce on 0. until end. Turn fast, no problem. Again, little. Yes. Until end, yes. Now switch off. Close the water. It's not so hot, 27 degrees, it will not melt. Okay, we close. Yes. Now we do the calculation.
So let us do the calculation. Now calculation table, what to write here, number 1, 2, 3, I will explain in sample calculation and then we will transfer your answer in the table for 9 volt and 12 volt. Now number 1, so no need to write this in the table. Heat flow area of the metal slab is same and it is A is equal to pi by 4 d square is equal to 4.91 into 10 to the power minus 4 meter square. Don't forget unit. Number 2, which I will transfer in the table also, heat flow. Heat flow is equal to Q is equal to voltage into current. Number 3. Once you finish the heat flow, then I will find the temperature difference in hot section and cold section. Temperature difference in hot section, so is equal to delta T 1 to 2, 2 to 3 or 1 to 3. You can choose any one. So I will choose 1 to 3 is equal to T1 minus T3.
So E is equal to 52.2 minus 49.4 is equal to 3.7 degrees centigrade.
So this is about the temperature difference in hot section. Similarly, I will find temperature difference in cold section is equal to delta T 6 to 8. So I will write T6 minus T8. I can choose any. 26.8 minus 23.1 is equal to 3.7 degrees centigrade. And sorry, change this answer. This is 2.8 degrees centigrade and this is 3.7 degrees centigrade. Now I can find number 5. I know the temperature difference. I can find out thermal conductivity of brass in cold section and hot section. Thermal conductivity of brass in hot section and cold section. So I can find both here 7 and 6. So K hot is equal to Q by A delta X 1 minus 3 1 to 3 and delta T 1 to 3 is equal to. So I can put the values. Q is 186.791 watt per meter degree centigrade. So similarly, 6, thermal conductivity of brass in cold section is equal to K cold is equal to Q by A delta X 6 to 8 divided by delta T 6 to 8. 141.355 watt per meter degree centigrade. Now my target is to find out temperature at hot phase of steel. T hot phase is equal to T3 minus T2 minus T3 by 2 is equal to 48.7 degrees centigrade. Now similarly I can find out 8 temperature at cold phase of steel is equal to T cold phase is equal to T6, now opposite plus the difference T6 minus T7 by 2. 27.25 degrees centigrade. Once you know T hot and T cold, we can find out last thermal conductivity of steel specimen is equal to K steel is equal to Q by A, again area is same, into delta X steel divided by T hot phase minus T cold phase is equal to Q 8.56, no change, 4.91 into 10 to the power minus 4, no change. And now the delta X steel is 0.03 divided by T hot is 48.7 minus 27.25, and the answer is 24.383 watt per meter degree centigrade. So first area is not going to change, so I will not write area. So here heat flow symbol Q, unit watt, write your answer for 9 volt and 12 volt. Then next heat flow colors, temperature difference in hot section, cold section. So you can write here temperature difference in hot section, delta T hot or T1 minus T3 control shade. Okay, delta T hot is equal to degree centigrade right here. Temperature difference in cold section, delta T cold, degree centigrade. Thermal section, thermal conductivity, thermal conductivity of steel is equal to K steel, you can write, so no plus. Okay, so you can transfer your answer here for 9 volt and 12 volt. Now we will move to the graph. The graph is important, and now how to plot, and we need to write the observation and review questions from the graph. So first we'll write, now first here we'll plot the graph temperature versus distance along the slab thickness. We'll choose on x-axis 10 lines is equal to 0.01 meter of the length of the slab, and y-axis 10 lines is equal to 5 degrees centigrade. Here we will mark the distance on x-axis, distance in meter with the arrow, and temperature in degree centigrade on y-axis. So line number 1, 0.01, 2, 3, 4. So 1, 2, 3, and here also from x-axis we'll choose, start from 20, 25, 30, we have temperature in degrees centigrade with arrow. Now let us start the lines. So first line will start from the 0 as a T1. So first line will be at 0. So this is T1. Okay. Then second line plus 0.015. The distance between two thermocouple T2, and distance between 2 and T3 is 0.015 plus 0.0153. So it will be 3. Okay. So this is temperature T1. So I will mark it here. This is temperature T2 and this is temperature 3. So I will go little back. We started T1 from 0. So distance for T2 is plus 0.015. So this is 0.015. Okay, so I make this line. Now T3, again distance is same, 0.015. So addition of these two is 0.03. So I mark the line at 0.03 here. 1, 2, 3. Now there is a T hot face at a distance of 0.0075. So we'll get addition 0.0375. So here I need to choose 3.75 here. Okay. Now the distance of stainless steel bar, stainless steel slab, the distance of thickness of the stainless steel is 0.03. So this is again addition. So I will get a T cold face at 0.0675. So this is 375, then 675 is here. Now the position of T6, the distance between cold face and T6 is 0.0075. So that will be 0.075. So it will come here 0.75 here. Then again 0.015 distance between T6 and T7. That is 0.090. Okay. Then last T8 again 0.015. So that will be a T8 will be 0.105. Okay, so I got this all points, so I will mark it here 3.75 here. So I will make a line. So this is T hot face, T cold face is 0.0675 here. This is cold face. Then again T6 0.75 here. 75, then 9, and then 10.5. This is a T3, and this is T hot face, and this is T cold face, and this is T6, T7, T8. Okay, so once we plot this, so again I will write here, the first is 0.015, this is 0.03, this is 0.0375, 0.0675, and this will be again 0.075. This is 0.09, and last is 0.105. Okay, now let us plot the temperature T1, T2, T3. Now first temperature is 52 point, so 52 point is somewhere here, 50.8 is somewhere here, 49 point somewhere here, then 26, this is 25, T6 is 26 here, 2 lines, then 25, 26 here, a small difference, 3 lines here and here 2 lines, and then 23 here. So 23 means 6 lines here. Yes. Join point T1, T2, T3 and extend it up to T hot face. Similarly, join T8, T7 and T6 and extend it up to T cold face. Now I got this temperature from the graph. I got this temperature from the graph as T hot face and by calculation also. So I can write in conclusion from T hot face from by calculation and T cold face by calculation and graph. Okay, then join these 2 points by a straight line, hot face and cold face, and this is used to find out the thermal conductivity of the steel. Choose any 2 points on hot section and find out thermal conductivity by graph by slope. So this is delta x. So here I can draw the horizontal line between dx is equal to 0.01 and dt is equal to T2 minus T3. Okay, same I will choose the point from this point to this point. Okay, so draw the vertical line. So here dx is equal to 0.01 and find out the temperature. Here it is 35, 37.5 around approximately, and this temperature is 45, 46 or 7, whatever from graph, 46.5 doesn't matter. So I get here dt for this minus this and dx, so I can find out thermal conductivity. Similarly for cold section, choose any 2 points, this and this, and write dx is equal to 0.01 and dt is equal to this is 6 and 7, T6 minus T7. Okay, so this is about the taking slope. Similarly do for the 12 volt. Okay, now we'll move to the, now for 9 volt dt by dx, write here T6 and dx and write the calculation, put for 12. 9 volt same 12 volt for intermediate section, and this is a steel section, intermediate section, steel section. So we can find out from there what I wrote here. So for here 9 volt I can write around approximately 46.5 minus 37.5 divided by dx is 0.01. So I will get the answer here. Similarly for 12 volt here I can do, and I can find this. Okay, for here for a hot section, dt is T2 minus T3 divided by delta is 0.01. So put this from table, right answer similarly. So we can review these questions. And for thermal conductivity of brass by graph, that measure the temperature gradient through cold section. Now thermal conductivity of from graph for brass. We can add for steel also, K steel. K steel is equal to from graph Q by A delta X steel by delta T from graph. Okay, so I can choose Q by A is 9, whatever this, and delta X 0.01, 8.56 divided by 4.91 into 10 to the power. So delta is 0.01 and temperature difference is 46 point minus 37.5. So I will get from graph. Okay, and already we calculated. So write the conclusion. Thermal conductivity of steel and brass is K brass Write the answer from A for anyone 9 degree. Write K steel, K brass is equal to by calculation, calculation by graph. Graph, write two answers. Now for K steel, write thermal conductivity dash by calculation and by graph. Number 2, as temperature increases, thermal conductivity increases. And you can check your result. So steel, thermal conductivity of steel is around 20 and our answer is 20 point something. So it is correct. So write this and submit next week. Thank you very much.